Physics review. Let's go. Let's do some physics today about some space game I've been making. Hello. Okay, now we're gonna do some physics, right? The game's called Planeta, right? You have a planet, and you're this little stick figure guy, okay? Now, in normal physics, we have this gravitational function called, so we have this body here, and, you have a pull between both of them. This guy is being pulled down by him. These two guys are getting attracted by each other. Let's call this planet A, planet B, right? So normally, you'd have, mass of A times mass of B over the distance squared, all times G, right? But in this case, we throw this out the window, and we're using our own little altered version of physics. So instead of having planets attract to each other, they're actually fixed in place. Instead, planets have a gravitational field. I assume it's a circle, right? But you have, gravitational acceleration of A, which might be something like, negative 5.0 meters per second squared. You might have the gravitational acceleration of B, which might be like negative 6.0 meters per second squared. And you might have your human here. In this game, our guy, he basically goes in circles until he jumps off, and he goes off in a tangential velocity out of the planet into the vacuum of space, where he's not affected by any forces unless he goes off at the right tangential velocity, and he ends up hitting the other planet's gravitational pull, okay? So, what we need to figure out is at what force does our guy have to jump to escape the gravitational pull of planet A and get to planet B.
Your battery's running low.
It's okay. We're gonna zoom in on the planet, right? It basically becomes flat. Force vector here is our f of g, and that's our vector that pulls towards the center. We have another force called f of j, and then we have our gravitational field is bounded by a hat. So let's do this. So now let's zoom in on the planet, right? We initially have planet A. So we just need to find what is the minimum force that we need to jump, so that way we get to the very edge of this person. We're using his head as his center of gravity. Let's say he's a stick figure, his sticks have no mass. F of j
Battery is at 15%.
Okay. F of j has to be greater than f of g. We're gonna give it a mass variable of m s for massive stick figure, right? So, and we'll give it this has a acceleration of a g, right? So we know that m s a of s has to be greater than m s a of g, right? We also know that we have a height,
right? And we're jumping up, and we need to get to this top, right? So we know that for the vertical thing, we have h equals the initial velocity times time plus
to a h times m divided by delta t, all of this plus f of g. And this would give us our jump force. So our jump force will really depend on how much time we're going to jump, basically. And that's about it. Everything else is a little bit extra besides that. Now we can get on to the actual simulation. So here's the actual simulation, right? So the game engine I'm using has a function that allows us to apply an impulse force to a specific object. In this case, I'm applying it to my player right here. And if I build up enough of a horizontal velocity, then I can jump, and then he goes over there. If I just jump regularly, he's not really going to have enough of a jump force. So when you're dealing with a planet, you're also dealing with the horizontal velocity. So when you have a planet like this, the horizontal velocity and the vertical velocity vectors are added together, which combines to a total velocity vector that actually allows it to escape the planet. It also needs a horizontal velocity component to actually give it enough oomph. Some planets have less gravitational pull, as me just moving across the planet causes me to jump. If we go with this one, right? This planet here, just jumping alone will cause you to escape gravity and fall into the abyss of space. So that was the physics of Planeta.